Thank you very much for the invitation. It's great to be here. And today I will be talking about reducing enteric methane emissions from dairy cattle. Let me see if I know how to use this. There we go. As you know, methane represents 11% of the total US greenhouse gas emissions. And methane is the second most important greenhouse gas after CO2. And enteric fermentation accounts for 27% of total US methane emissions. And enteric fermentation from livestock is actually the second most important source of enteric methane emissions after natural gas and petroleum systems. As you know, methane is a very powerful gas, greenhouse gas. It has more than 80 times the warming power of CO2, and in the short term, methane sets the pace of global warming. Now, beyond the impact of methane on global warming, enteric methane represents a loss of energy, about 6 to 12% of gross energy intake. And enteric methane should be recognized as an energy sink, energy that could otherwise be available for growth or production. Therefore, there are multiple benefits associated with reducing methane emissions from dairy cattle, including reduce the environmental impact of dairy farming and at the same time improve production efficiency. So given the importance of methane emissions, at the end of last year we put together a large research grant entitled Integrating Genomic, Milk Spectrometry and Microbial Manipulations to Mitigate Enteric Methane Emission from Dairy Cattle. We are a multidisciplinary team, including dairy cattle geneticists, dairy cattle nutritionists, and microbiologists from multiple institutions, including the University of Wisconsin, Michigan State University, Iowa State University, the University of Florida, and the USDA. And our overall goal is to reduce enteric methane emissions from dairy cattle by combining selective breeding, the use of milk spectral data, and rumen microbiome manipulations. Note that this is basically the same team that has developed and implement a national genetic evaluation for dairy cow feed efficiency, and the resources, the knowledge, the experience, the project management, and the communication gained in the past 12-13 years will be now leveraged to reduce methane emissions from dairy cattle. This project has been funded by the Greener Cattle Initiative. As you may know, the Greener Cattle Initiative is a consortium created to support research that enables the mitigation of methane emissions. Here we have the founding members of the Greener Cattle Initiative. I want to thank the Greener Cattle Initiative and its program director, Juan Tricarico, for supporting this research. As you can see here, the Council on Dairy Cattle Breeding is one of the founding members, but we also receive matching funds from the Council of Dairy Cattle Breeding. So I want to thank Joao Dur, his team, and the Board of Directors for supporting our research. So our plan is basically to phenotype 4,000 lactating cows in 6 research farms over 3 years. So we will be measuring methane emissions and feed intake daily, and of course we will measure milk yield and milk composition to compute milk energy, and we will have body weight, and we will have spectra data, and we typically run our trials between 6 and 8 weeks, between 50 and 200 days in milk. And as I mentioned before, our goal is to tackle methane emissions combining selective breeding, the use of spectra data, and rumen microbiome manipulations. We want to be the foundation for the development of genetic evaluation for methane emission traits. We want to evaluate the use of spectra data to predict methane emissions. And we want to reveal the composition and activity of the rumen microbiome of cows with extreme emissions, low and high methane emissions. And at the same time, we want to decipher the relative contributions of the cow and the microbes to produce methane, and for that we will do some cool trials where we'll exchange ruminal contents. Regarding phenotyping, as you know, different techniques have been developed to measure methane emissions from respiration chambers. They are very accurate, but at the same time they are very expensive and labor intensive, and hence are limited to a few animals. We also have the SF6 technique that is somewhat more scalable than the respiration chambers, but they need daily handling of animals, rumen bolus, and measurement of gas in the lab. We have the green feed system. We have sniffers. The sniffers are very popular in automatic milking system, and we have even laser detectors. So we decided to use the green feed system. The green feed system is a practical system that delivers reliable estimate of enteric methane emissions. The key to obtain reliable estimate is to obtain many short-term records measured at different times of the day for multiple days. So basically the idea is to obtain multiple visits per day at different times of the day over multiple days. And our cows, they have access to green feed units 24 hours a day during 6 to 8 weeks. This is our setup at the UW Dairy Research Center in Arlington. This is our famous Pen 30. You can see here the blue gates where we measure daily feed intake. And we have now 2 green feeds where we measure daily methane emissions. This is data from our very last trial. We evaluate methane emissions in 58 multiparous Holstein cows during 6 weeks. As you can see here, multiparous cows produce roughly 450 grams of methane per day. But what is very cool here is that there is a very large variation in methane emissions across animals. We have animals that produce more than 600 grams of methane per day in one extreme of the curve. And we have in the other extreme animals that produce less than 300 grams of methane per day. And as you know, genetic selection requires variability among animals, and the variability observed in this small trial strongly suggests that genetic selection is one way to reduce methane emissions. In fact, selective breeding is a promising tool to mitigate enteric methane emissions. Methane emission traits are heritable traits with heritabilities between 15–20%. But methane is difficult to measure, right? Methane is difficult, it's hard, it's expensive. Now, in the genomics era, genomics has facilitated the selection for traits like methane emissions because we can phenotype a relatively small number of cows that at the same time we genotype, and then we can use this reference population to predict genomic PTAs for the entire population. So one of our goals is to develop a reference population for methane emissions, develop genomic evaluation for methane emission traits, and finally facilitate the incorporation into selection indices. Again, we are basically the same team that developed a reference population for dairy cow feed efficiency, and now we will develop a reference population for methane emissions. Now, talking about different traits, there are alternative methane emission traits. Of course, we have methane production, defined as grams of methane per day. And then we have methane yield and methane intensity. Methane yield is defined as methane production per kilogram of dry matter intake. and methane intensity is methane production per kilogram of energy corrected milk. These two are ratio traits. Ratio traits, they do not have good statistical properties. We do not like ratio traits. Changes in ratio traits are hard to implement and interpret. So an alternative is to use residual methane. Residual methane production has the same meaning as residual feed intake. It's basically methane production regressed on or adjusted for dry matter intake, metabolic body weight, and or milk energy. So we have here two alternative methane production traits. This is data from our last trial, the 58 cows that I showed you before. Each dot here is one cow. So in the y-axis we have residual methane adjusted for dry matter intake, and in the x-axis we have residual methane is methane production adjusted for metabolic body weight and milk energy. So again, each dot is a cow. We have in the bottom cows that are producing roughly 100 grams of methane less than predicted. And on the top we have cows that are producing up to 150 grams of methane more than expected. What is very interesting here is that these two methane production traits are highly correlated, with correlations around 95%. Please note that residual methane, methane production adjusted for dry matter intake, can be measured on research farms, but residual methane adjusted for milk energy and metabolic body weight can be measured in commercial farms, and we are working on that right now. I told you that we will work also with milk spectra. As you know, spectroscopy is a very powerful phenotyping tool. Just think about it: high throughput, low cost, non-invasive. We can get real-time predictions. And milk spectra has been used to predict complex traits, including energy status in lactating cows, metabolic profiles in lactating cows, health status, and fertility, among others. And there is a very recent study from Canada. It's a study that uses a small data set, but the author suggests that it's possible to predict methane emissions using spectra data. So our goal here is to determine the value of using spectra data to predict methane emissions. We will have more than 4,000 cows with methane emissions, and we will have the same cows with spectra data, so we will be able to determine the value of using spectra to predict methane emissions. Finally, we will work with the rumen microbiome of the cows. As you know, enteric methane is formed exclusively by methanogens in the rumen. Now, the interplay between the cow genome and the rumen microbiome is complicated, and we plan to reveal how the microbiome composition and activity affects methane production, but we also want to assess the relative contribution of the cow genome and the microbes to methane formation. And we can do that if we use structural equation models and graphical models. Just to give you a little flavor of what we can do, this is a research that we are doing right now, but with feed efficiency traits. So we have dry matter intake, milk energy, and residual feed intake. We have roughly 450 cows, and for each cow we have the genome, and we have the rumen microbiome. So basically in blue you have the typical heritability, the amount of phenotypic variance explained by the additive effects. And in green you have the result of a model that incorporates at the same time the cow genome and the rumen microbiome. And as you can see here with the little m, that is the amount of variability in the phenotype that is explained by the rumen. So the rumen microbiome explains between 20 and 30% of feed efficiency traits. The other cool result is that the direct heritability, that is the amount of phenotypic variance explained directly by the genome, is smaller than the total heritability, and that means that the rumen microbiome mediates part of the cow genetic effects. And in gray, those are results of a model that also include an interaction between the cow genome and her rumen microbiome. And as you can see, this interaction term explains part of the variability in the rumen in the feed efficiency traits. Our solutions, we plan to deliver multiple solutions. We want to be the foundation for routine genomic evaluations for methane emission trait in US dairy cattle. As you know, contrary to improvements in nutrition and management, changes achieved through genetic selection are incremental, cumulative, and permanent. That makes genetic selection for reducing methane emissions a very effective strategy. We will also deliver spectra-based solutions. If milk spectra is a good predictor of methane emissions, then we can use milk spectra to increase the accuracy of genomic evaluation for methane traits. But even more important, we can have real-time predictions of methane emissions. We can use a spectra to optimize cow management in the dairy farm. With those real-time methane emission predictions, we will be able to assign some of these high methane emitting cows to some specific diets. Finally, we will deliver microbial solutions. At the end of this project, we will have a deeper understanding of how the host influence diversity and activity of methanogens, and we can use this knowledge to target strategies to reduce methane formation in the rumen. With that, I want to thank again the Greener Cattle Initiative and the Council on Dairy Cattle Breeding for funding this research. I want to thank my colleagues at the University of Wisconsin-Madison. They do all the work. They deserve all the credit. I want to thank the rest of the team. You have the list of the team here. Thanks for your attention, and I think I can receive some questions. Thank you.